All right, so here's the next part now that I erased and reset. Okay, so suppose engineers estimate that 10% of the mechanical energy of the car will be dissipated as heat due to friction, okay, between A and C, and that their design requires the force exerted by the track be half the weight of the car at point C, okay? To what height should the initial A be changed to meet this requirement, all right? So let's think about what's changing here. Okay, so first of all, we have to add some for E therm, okay? So normally if there was, that would just like subtract from the kinetic energy, right? The gravitational is still the same, but you know, if there's friction, it's just going to make it slower. It's going to impact the kinetic energy, okay? But we actually want to get more kinetic energy, right? Because if we're going to need a normal force now here on the track, that's going to mean it has to be going faster to support that increased centripetal force, okay? So if I need to account for friction plus make the car faster, the only way to do that is by adding some more height to the beginning, right? Or adding something to make it faster, okay? So let's just say maybe that's 3, 4, 5, okay? All right, so the basics of the equation are still the same, okay? Except for now I have to add thermal energy to that picture, all right? Since they're not really giving us any information about this other than this percentage, okay, the easiest way to do that is just to say 90% of what you started with, right, is what you end with, okay? So that's kind of how I'll account for that 10% by just saying that I'm only going to use 90% of what I started with, okay? All right, so other than that, everything's the same except for at the top of the path here, okay? So you had your mg from the car, but now they're saying they also want you to have a normal force, okay? So now my Fn plus my mg is going to be my centripetal force, okay? Or half mg plus mg is mv squared over r. Oops. Why does it always do that? Okay, so then all those m's are going to cancel, right? So, oh no, yeah. Okay, so when I add these together, half g plus g is going to be 3/2 g, all right? So my velocity then is going to end up to be 3/2 gr square root, okay? All right, and then when I plug that all in, I'll see that that's going to be 2.74 meters per second, right? So that's faster than before, which I would expect because that centripetal force is bigger, right? Because I have to put a normal force in. Okay, all right, then all I have to do is just crunch out all these numbers. So 1/2, I'll just write mv squared plus okay, and I would go ahead and write this step, right, even though it kind of seems like a hassle because you might get points on the AP test for writing that. Okay, so you don't want to skip that because if you make a mistake in your numbers, you're going to lose that point that you might get for writing it like that. Okay, all right, so 0.9, 1/2, all those m's are going to cancel again. Hallelujah, squared plus 10hi equals 1/2, 2.74 squared plus 10, 1.2. Okay, all right, so let me just do this. I'm certain that you can crank the math out by yourself. Nope, 0.5 times 0.2 squared, which was like literally nothing. Okay, so 0.9, 0.02 plus 10hi equals 3.75 plus 12. Okay, so 15.75 over here, and now I'll distribute in the 0.9. So I get, again, a big waste of 0.018 plus 9hi. Okay, so 9hi is going to be, like, honestly, do we even care about this 0.018? Like, it's not even going to matter. Oops, 15.75 minus 0.018. Oh, 15.73. Ooh, big difference. Okay, divided by 9 is 1.75 meters, okay? So this is going to come out higher than it did last time, which we would expect because you need more energy to start because you have to account for the friction plus the increased velocity because now you want more centripetal force, okay? So that number should come out higher. If it doesn't, then you'll know you did something wrong. Like the first time I did this problem, when it didn't come out bigger, then I knew something was wrong. So this is take 2, okay? Yeah, that's it.